stochastic versus deterministic modeling in seismology, where obviously there's both threads, and to what extent have people tried to bring them together in a productive way, and what have been the obstacles, if people have tried, what have been the obstacles to doing that, and so why are there still people doing largely, various point process stochastic models, and then people doing complete deterministic models as opposed to hybrids.
Very good question. I think, as I interpret it, is there a middle ground between the deterministic and stochastic approaches? And a lot of people, including myself, are trying to build such a middle ground, but the division is more than just a philosophical one. The division is, to some extent, a division between instrumental, reproducible data that come from seismic networks and much less reproducible, harder to interpret data that come from trenching of faults and things that are a bit more qualitative, less easy to archive and say this is what the data tells us. And generally, the more deterministic people are dealing with the older data. There's less of it, and the stochastic people see a lot and can get statistical distributions and things like that. And there are, big philosophical differences. And we really argue about what is the fault. Can you treat it as a surface or a volume or a fractal sort of generalized surface with a different dimensionality than simple planes. And even what is an earthquake? When you look in detail at an earthquake, you see that the deformation along whatever you think the surface is stops and starts. And if you have higher frequency data, you see what in low frequency data it looks like a continuous rupture starting in one place and throwing down the fall. You see lots of little pieces of it. And that leads to the question, can you associate a magnitude with something like that? There's a bunch of pieces in which the spectrum takes place in different places at different times. Could even model that as sub-earthquakes. Give each one of those a magnitude and the name and divide at a time. But then as you look at more detail, you see that the animal still keeps. And people from the more classical, well-operated and more classical mind frame don't seem to keep them. There are big earthquakes, we have these catalogs of them, we know their magnitudes, and we can analyze those. So it's pretty hard to bridge a gap when you have a viewpoint that when you look at something that seems simple to someone else, it is really not a unit. Maybe you could follow up with your reaction in other fields.
Well, we've just seen people talking about the atmospheric sciences, how bringing variability intrinsically into the model has helped in reproducing certain features of the observable system. So is it the case that even if all you're interested in is motions over larger scales, so that the individual little earthquakes don't matter so much, could there be an analogous result here, that if you try to stochastically model some of the minor events, you actually end up modeling some of the larger scale processes better because of it? Now, maybe the situation isn't analogous at all. So I'm kind of arguing from analogy, which doesn't necessarily work.
Well, I think your analogy does work, and I think there is fruitful ground for bringing a stochastic viewpoint onto the more deterministic picture. I mean, faults do exist. Earthquakes like to happen, not always, but they prefer that if they can. And I think by sort of starting with a simple deterministic point of view and trying to introduce some reality into it, I think there is fruitful
I think it perhaps leads to some interesting stochastic process modeling. We have a deterministic model which is driven by some set of Gaussian process, but driven by some kind of point process in space and time, and that seems to me there could be some interesting challenges, mathematical challenges there.
Just want to add that although we are not shown here, certainly not in my work, but there are a lot of other models in different branches of earth sciences like hydrology that has stochastic process built in deterministic models. Some similar issue in isospheric dynamic models.
Just a general, just a general comment about, I mean, this is sort of fatally obvious, I suppose, but one of the general comments you can make about nonlinear dynamical systems, whether they're hydrodynamical systems or otherwise, is that they exhibit threshold behavior as a consequence of the instabilities that they support. And so one can and should argue that the deterministic predictions you make with a deterministic level model, if they're not robust in the presence of stochastic perturbations, then you can have no faith in them at all. So, and I think that's a very general comment that one can make about nonlinear dynamical systems in general, and it really obliges us to take noise seriously.
Noise.
Yeah.
Is it a bad noise?
Random numbers. I have a point, question. What kind of data you for example, for the earthquake prediction, what kind of data you guys need to have better predict or better understand the mechanism of the earthquake, so we can use the data to improve the model when we predict the earthquake. So what data is needed? Basically, that's the question. Yes. Or just say earthquake.
There's a different aspect for earthquakes. If you're talking about earthquake forecasting and prediction, the primary data is earthquake history, what happened in the past. That allow you to try to find a pattern and give you a hint of what's going to happen in the future. We have major challenge there because the record of history most time is too short to be very useful.
So you are thinking just do this kind of time sequence fitting so you can predict earthquake? That sounds weird to me. Because I understand.
Basically, like a lecture in a pop field example, you have a sequence of events that has some kind of regular recurrence interval. That if that's all full, if that's true, that'll give you a base to make predictions that in another 22 years, in that pop field place, you will have a magnitude of 6 earthquakes.
I have a couple.
Oh, I was just going to ask a very naive question. I'm not a seismologist, but on this recurrence time. So if you have like a major earthquake and things just basically completely jumble up, why would you imagine that the recurrence time would make any sense? I mean, now all of a sudden you have a totally different physics. As an outside observer, I just don't see how this makes sense. If the Earth stayed exactly the same, I would say, okay, well, maybe this recurrence time makes some sense. But I would imagine that there's earthquakes that are big enough that everything gets rearranged. So what's the point of this recurrence time?
There are no earthquakes which are big enough to change.
Well, change them enough, not to change Europe. Okay, but you know what I mean. I mean, it's just a naive question, but I just wonder why this is important.
You're way ahead.
No,
I'll give you my 2 cents. There's at least a two-sided view. One side says that earthquake happens when fault is. If the fault is a plate boundary, another fault is loading at a constant rate, because geological record shows that the relative plane of motion has not changed in the past few years. So if you have a fault that's being loaded at a constant rate, and in addition to that, if you can assume that one segment of the fault tends to rupture entirely every time when it reaches that critical threshold, then you can argue for this typical, something called characteristic earthquake. And because the energy input is at a constant rate, then the earthquake, which is a release of energy, needs to be at a constant rate. So that's the ground to think about a kind of periodical occurrence of the event. On the other hand, you can argue, as I was showing here, that the fault rupture may not repeat on the same segment every time. Sometimes just a small part of the ruptures. Sometimes the whole fault segment ruptures. We don't know exactly what control this, where they stop, where they initiate. There's many factors to get done, but we don't know which one is really controlling. If in that case, then you don't have a very good ground for recurrence interval. And some people argues and inclined to classify that this concept of recurrence interval is questionable.
Yeah, I'll second that. Before you can talk about recurrence interval, you have to say recurrence interval. And many of the papers that have reference to recurrence interval, we're talking about recurrence interval of a selected sequence. They need recurrence interval of this group of earthquakes that I picked up on the catalog, and here they are. And of course, you can talk about repeat times of those, but I don't believe that has any significance at all when you run it forward, unless you can show that those events somehow have some common property that a future event is going to have, and you'll know when it's occurred rather than have to say, gee, was that it or not? And most of the time, you're in that question. We're going to come back to this question about earthquake prediction, because I know that there's interest in that based on yesterday's discussion and some of this. I distinguish and insist on distinguishing between earthquake forecasting, which means tell me what we know about earthquake occurrence, trying to quantify this, and prediction, which goes beyond that and talks about a single earthquake and high probability that justifies you doing something that you wouldn't normally do. Escaping or owning an experiment or doing something that is sensible only in a time period in which you think something urgent is likely to happen. For forecasting, there are three big forms of data that I think inform just about everything we do. The earthquake record, the geodetic strain accumulation, and faults. And those go in timescale where the earthquake record comes every day. And geodetic deformation is generally measured in timescales of years or for decades. And the faults then reach back tens of thousands of years. We can weave those together. No one of those succeeds by itself. The models put all those together. From that, you can get pretty good spatial and temporal and magnitude relations about earthquake occurrence. Earthquake prediction requires something that I don't believe we have. In fact, I nearly got excommunicated by writing with some colleagues a paper about 10 years ago, whose title was Earthquakes Cannot Be Predicted in Science magazine. And people were mad as hell. And I suggested to people that they just call the Caltech psychology lab, and you get a recorded message that said, here's what happened today, Earthquakes cannot be predicted. So I didn't think it was a practical. Lots of hopes for various electrical signals or things that might recognize changes in the stress level. But the fact is, those changes in the stress level are pretty well recorded by earthquakes, by strain that takes place that we measure genetically, or motional faults that we know about already. So it's pretty hard to get beyond the simple things that gives the background issue.
I have a comment on that.
Oh, hornet's nest.
And that is the recent work, it's not my work, I'm a mathematician, but I've been interested in this. And it's an entirely different way to think about geophysical data. And that is to look at the noise of the data, look at what the seismogram records, and not be interested in the major events, but be interested in what happens more or less on a steady-state basis, the noise. And if you take this work was done, started about 10 years ago. If you look at the noise that is generated in the seismograms and you form cross correlations from pairs of seismic stations, from seismograms from seismic stations, then you get a very good estimate of the Green's function, or the travel time between these two stations. Very accurate estimation of that. The accuracy of the estimate of the travel time between two seismic stations, which tells you something about the geology underneath, is remarkable. It depends very much on the bandwidth of the noise that is generating, of the noise signal that is recorded and how it's generated. Now we know, and it's been known for a very long time, that these noise signals are generated by microseisms in the about 0.5 hertz to 5 hertz range. In other words, for the breaking of the ocean waves on the coasts around the world. And this is a steady source of noise that goes all the way around. And most recently in Réunion, I think about a year ago, you can probably know this very well, a French group of scientists put around the volcano seismic stations, and by systematically forming cross correlations, they were able to monitor by estimating the travel time and the change in the travel time, the estimated travel time over a period of time. They were able to anticipate the onset of a volcano. This is remarkable, and I'm in a meeting like this, and nobody's talking about it. You're waiting for a mathematician to tell you this. So here I am, I'm telling you this. Okay, I have worked on the theory behind this. I wasn't going to talk about this. I talked elsewhere about this. I didn't realize that this is what the interest was. But I can tell you, Michel Campillo in France, in his group in Grenoble, they have tried that with earthquakes. The gentleman over here asked, what should be measured? And what they say is, measure the noise and form cross correlations across a fault and track the noise cross correlations, their changes over time. And that should be a good predictor of the onset of a breaking of a fault, because it tracks the tension, changes the speed of propagation on small distances, and it gives you a signal as to the pressure change, the structural changes that pressure has as a consequence. This has failed. It has worked very well with. It has failed up until now. It has worked very well with volcanoes, but it hasn't worked on the earthquakes. Campillo did a very profound study. He looked at historical data where there is instrumentation around faults. For example, park feed. And he did one in China and several of them where he had instrumentation and data. And he formed cross-correlation of the historical data. And he found that about 70, correct me if I get it wrong, I think it's 70 or 75% of the historical earthquakes could be predicted on this. But some of them could not be predicted at all, like the 1976 earthquake in China, for example. Could not be predicted at all. So there's a profound movement that is changing the scene completely in this earthquake prediction business. I don't know where it's going, but mathematically and quantitatively, it's very exciting and poses some very interesting questions. So now I can hear your reactions.
I agree with you in very large part that it's a very promising field, and I think especially for volcanoes where you know where the target is, and where generally the deformation that leads up to an eruption is.
What about Parkfield? Parkfield is loaded with instruments. I saw a documentary not long ago.
Can I finish?
Let me point out about Parkfield.
You asked for my reaction. Let me give it to you, and then I'll give you a chance to respond.
All right.
I don't agree with your assessment of how successful it's been in being able to, or that it should have been able to predict earthquakes that happened in the past. The studies at Parkfield are among the best in the world, is one of the best monitored places, and there were not evident changes in velocity leading up to Parkfield.
Was it tracking cross correlations?
Including cross correlations.
I have not seen that study. I'm quite wrong.
As you comb through the data, you of course can find variations in an earthquake that you know about, and you can associate some variations and say, I should have recognized that that variation was coming before an earthquake. But when you look at a place where you don't know that earthquake is happening and you see variations, in other words, to say that it's got predictability is a lot more difficult than simply to say I recognize something and it happened before an earthquake. So that's my reaction.
Okay.
I agree, it's promising, and
I think it has a long way to go. It's very new. Only it has to be tested. But I want to say that the tracking of cross correlations is a new tool. It hasn't been there for until the last, say, 5, 6, 7 years. It wasn't done before. I'm not exactly sure why microseismic research was done in the past. I have to do my own homework on this. It started in the 1940s in France and elsewhere. There's a very important work that was done by the British in the 1950s, which is the source of this noise in the seismographs. But the systematic tracking of cross correlations for predictive purposes is very new. So it would be premature, as far as I can tell. I heard Campillo speak about this. He addressed the plenary session of the AGU 2 or 3 years ago, and that's where he presented his results. And I'm quoting from memory. But I would say that there are other things. The understanding, making this into a predictive tool, that's an entirely different. Of course, it has to go through a lot of stages. I'm not saying that it's going to be ultimately successful or not. But we know where the earthquakes are happening. Why has Parkfield been seeded with instruments for the last 40 years? Because people expect it to happen there. It's not like the volcano is different. We do know that the San Andreas fault is where it is, and Parkfield is a dangerous place where it might happen at the earthquake. So, and we have put the instruments there. I saw a documentary, just to lighten up a little bit the discussion. I saw a documentary of scientists. It was shortly after in the 1970s, busily putting these very bulky instruments from that period all around the Parkfield area. And then 10 years later, they looked a little grayer, and they were putting the nicer instruments, and then 10 years later, they looked a little bit grayer, and so on, and nothing happened.
I have a suggestion. Why don't you and I listen to some other people?
Actually, we're just about to start this next discussion. It's relevant to this discussion.
Yeah, I just want to point out it's very important to realize that volcanoes are a very different situation. That volcanoes are driven by fluid motions. So, I mean, we understand the macrophysics of it a great deal better, not perfectly. Earthquakes and volcanoes result from those fluid pressures. And as a result, our ability to predict volcanic eruptions is pretty good. I mean, it's not perfect, but it's been surprisingly good. And it's been good for at least 15 or 20 years now. So what we're using is the earthquakes to monitor stresses and deformation that are result from these fluid motions. It's a very different and, in some sense, a much simpler system, which is why volcano prediction is basically a recognized body of knowledge. It's not perfect, but the vast majority of times now they are making calls. They're not making long-term calls. They're making calls a few days in advance, but they have enormous ground deformation. I mean, you're dealing with meters of deformation.
you're dealing with gas eruptions, you're dealing with a large class of things in which earthquakes are there. So I mean, it's in a sense, it's a much better understood problem. It's also a problem which is not solved, but which has been a lot of progress. But it's just an overall. So it's not, you can't really translate one to the other.
Yeah, as illustrated by the famous argument between Allegra and Tazier.
Sure, but I mean, for example, in Tubo, they were able to call. A lot of times they've been calling for evacuations on about the right time scale now, and it's not perfect, but it's surprisingly good.
It's worth noting that although volcanoes are simpler systems because they're fluids, there's always a lot to be learned about fluids. And put in mind particularly the nature of the pre-eruption tremors, which sometimes show characteristic, almost harmonic frequency. And Mark Jelinek has done a lot of interesting work on the fluid dynamics of that, actually tracing the tremors to the boundary layers, the instabilities, shear instabilities in the boundary layers where the magma is rubbing up against the channel. So,
No, I absolutely agree with that.
Yeah, well, first of all, I'd like to point out that since George Papanikolaou has been so modest and only referring to other people's work, I want to say that with respect to the discussion we've been having before about deterministic versus stochastic, a lot of the work that Andy might have talked about, is based on some stuff that George did 40 years ago, in which he showed that you can very well model some high-frequency deterministic phenomena, by stochastic ones. And so, again, nature is neither deterministic nor stochastic. It depends on which way it's convenient to model. Now, I do want to congratulate Leanne and you on the fact that you showed that very clearly that simple model of Harry Reid. Basically the idea is that these are relaxation oscillations. Okay. Now, I again want to tell you a story which isn't new about why it's so hard to predict these things. Now, it's interesting that Van der Pol, who was working for Philips, everybody knows the Van der Pol oscillator, right? So Van der Pol was working for Philips in Eindhoven, and he formulated this model of, I forget what it was, diode or triode or something, and Philips was so happy with him that they allowed him for the rest of his life to do what he wanted. He was also an interesting guy, and he was interested in lots of stuff, music and so on. And he once gave a talk to the Scandinavian Medical Society, in which he explained the difference between harmonic oscillation. That talk is remarkable because he was talking to medical doctors, and there isn't a single patient. Okay? But he explained the difference between relaxation oscillations, and the ones that we all learned about in kindergarten, linear harmonic oscillations. And he basically gave an explanation about why the relaxation oscillations tend to be what we call today chaotic. He said there is a threshold. It goes up slowly, it reaches a threshold, collapses. There's what we would call today sensitive dependence on the initial state. Okay? The time when you reach the threshold, the recurrence time that we're talking about, is a sensitive dependent on the initial state. Okay? So, of course, in the fault networks and so on, there's a spatial temporal element which is not in a single scalar, etc. But there is nothing intrinsically unpredictable. I mean, this is, I'm sorry, but this business of volcanoes are predictable and earthquakes are not, it's simply voodoo, okay? I mean, we are going to learn more about earthquakes, about fault systems, and we are going to learn, we need all the geodesy and all the stuff that you talked about later. But the fact that, there's something that is intrinsically unpredictable. There is no perfect white noise, I mean, that's the only thing that is truly unpredictable is perfect white noise. And there is no such thing in nature.
Maybe to present a slightly different view on the
Hallelujah.
formulate differently is, would be to say that if we knew at which stress level the earthquake started and at which stress level they ended, we would be able to predict earthquakes. Because we don't know either the initial yielding stress or the final frictional stress. These two are probably somehow stochastically related. The exact prediction of the timing of the next event defined in a specific place and with a specific magnitude maybe never be able to.
I didn't say you'll be able to predict today exactly which magnitude earthquake will happen in 2077 in such and such a place. That's not what I said.
Right. So that brings us back to the point that Dave raised, making a very careful distinction between predictions and forecasts. So typically in this community, forecast is something that is happening on timescales of tens of years and perhaps longer. And by prediction, and the community really tries to avoid the word prediction, is something which is short-term and specific to a certain area. And that is something that we
In meteorology, we have at least half a dozen words to indicate, different shades of poor predictability. There's numerical weather prediction, which is sort of good to a few days over smaller areas, and there's forecasting, and there's foreshadowing, and there's prognostication, and there's Nostradamus. But, there's some version of something that you can say in advance. Okay. I mean, the use that you made in the solid Earth of forecast and prediction is exactly the opposite of what the one that we do in meteorology, and it doesn't matter. As long as you define what you mean, and you can do it, and you can verify it, it's wonderful.
All I'm saying is that the fundamental underlying physics may be such that this process may not be deterministically predicted.
I didn't say deterministically. Nothing in meteorology is deterministically predictable. Did you notice that? I mean, did you ever look at the weather forecast when you try to do your suitcase?
Well, you're in a much better situation because at least you know the constitutive equations. We do not know constitutive equations for structure dynamics. That's one of the main problems. Going back to this distinction between volcanoes and earthquakes and the issue of precursors, the main difference may be that in case of volcanoes, things are happening in the volume, and in case of earthquakes, things are happening, if not on a mathematical plane, but at least on something which is close to a planar surface. And this means that changes in physical fields may be simply very difficult to detect. So there were many previous suggestions that there are observable precursors based on variations of seismic velocities. Those proven to be inaccurate. And there may be, again, a very good physical reason for why such changes may not be observed, simply because things are happening on such a small scale, and we have no idea of predicting how this cascade will evolve, that this is something that is going to be very difficult to track. So one thing that I think is useful to make a distinction between the deterministic models that are probably related to longer time scales and kind of geodynamic models that people use to explain geodetic fields, for example. So these would provide stress and rates, but then the seismogenic process itself is a stochastic process, and the link between these two is something that we have